Hi everyone. In this video, we're going to talk a little bit about transforming and translating the graph of a function. First, we're going to talk about translating the graph of a function. Translating just means you're gonna take the graph of a function and you're going to either move it to the left or you're going to move it to the right, or you can move it vertically or vertically by moving it up or down. Okay. So really, it's just you're keeping the shape of a graph. You're just moving it in some direction or some combination of directions. Okay, you're not flipping it. You're not stretching or shrinking it. You're just moving it around. You're pushing it around on the graph. Okay, but there's a few rules we have to follow when doing this. So if we want to do a horizontal translation, if we want to go to the left, if we're given some function f of x, we want to go. Sorry, we'll start with the right. If we want to go to the right, a units, where a is just some positive number, we're going to graph f of x minus a. Okay, seems kind of counterintuitive there, but we'll see why this works here in just a few minutes. To graph f of x to the left a units, we'll graph f of x plus a. And for a vertical translation, i.e. going up or down, if we want to shift the graph of f of x up b units, we'll graph f of x plus b, where b is on the outside of the parentheses. And if we want to go down b units, we'll graph f of x minus b, where again, b is on the outside of the parentheses here. Okay, so these are some rules to remember. These are probably ones that are worth just memorizing. Obviously, it's important to understand how they work, but for purposes of tests, this can be helpful to just know this stuff as a fact to draw from memory here, okay? It'll help you get through problems fairly quickly. So let's say we are given this example. We're given a function f of x equals x squared, and we want to shift this graph up 2 units and to the left 3 units, okay? So in order to shift up, we're going to graph f of x plus 2, or plus 2 is on the outside. So up will be given by f of x plus 2, and left, we're going to go to left 3 units, so that'll be f of x plus 3 on the inside. So if we combine these two, our new graph will be f of x plus 3, and we have plus 2 on the outside. Okay, so this will be given by, so we can write this as f of x plus 3 plus 2 is equal to x plus 3 squared plus 2. Okay, so let's go ahead and find our points. Let's do a little point chart here. We can plot a few points and get the basic shape of this, and we'll see why this works. Okay. All right. So first, let's plot the point. Let's see what happens if we plot negative 3. So if we plot negative 3, we'll get negative 3 plus 3 squared plus 2. We just get 2, right? Negative 3 plus 3 is 0. 0 squared is 0. Plus 2 is 2. So we know that the point negative 3, 2 will be one of our new points. Okay, and the graph in blue here is the original graph that we were given. So we have initially f of x equals x squared. So there we go. What if we plot maybe 1 point on either side of this? Let's try negative 4. So if we do negative 4 plus 3 squared plus 2, we get negative 4 plus 3, that's negative 1. That's negative 1. Negative 1 squared is just 1, plus 2, that's 3. So we'll get the point negative 4, 3. Okay? Let's try negative 2. So if we do negative 2 plus 3 squared plus 2, we'll end up with 1 squared, which is 1 plus 2. We get 3 again. Okay, and if we try maybe the point negative 1, we'll get 2 squared, which is 4 plus 2, which is 6. So we'll get the point -1, 6. Okay. Hopefully we're seeing kind of a pattern here. Looks like we're kind of getting the same shape as the other one. It's just been moved. Okay. So then we'll have, let's try maybe -5. Okay, that'll be -2 squared. Again, 4 plus 2 is 6. So -5 will give us 6 as well. So if we trace this out, we're going to get, again, basically the same graph. Again, it's just now we have moved up 2 units. We've gone up 2, and we've gone to the left 3. Okay, which is exactly what we wanted. So we're kind of demonstrating why these rules work here. Okay, let's take a look at this one. Here we have the graph P of x equals the absolute value of x, and we want to shift it down 3 units, okay? And we want to shift it to the right 1 unit. So down is going to be given by P of x minus, went down 3, minus 3, okay? And then if we want to go to the right, this is going to be given by P of x minus 1. Because remember, it's kind of counterintuitive here if we're going left to right. Take a look back here. If we want to go to the right, we do f of x minus a. Okay, so we'll do P of x minus 1 because we're going to the right 1 unit. We'll see why this works. So combining these, our new graph is going to be P of x minus 1 minus 3. Okay, so let's plot some points here. P of x minus 1 minus 3, that'll just be an absolute value of x minus 1. And then we'll just have minus 3 hanging out over here. Okay? All right, so let's go ahead and let's just start with the point 0 and see what happens. So if we start with the point 0, we'll have 0 minus 1, or -1, minus the absolute value of -1 minus 3. So the absolute value of -1 is just 1. So 1 minus 3 is -2. Okay, so the point 0 will be -2. Okay, this is good. We wanted to shift it down 3 units, so this is a good start. Let's try maybe the point -1. So we'll have the absolute value of -1 minus 1 minus 3. So -1 minus 1, that's -2. The absolute value of -2 is 2. 2 minus 3 is -1. Okay, let's try maybe the point 1. So if we have 1 minus 1 minus 3, we'll get the absolute value of 0 minus 3, which will just give us -3. So the point 1, -3 will be one of our points. And let's try maybe one to the right of that and see what we get. Maybe if we do point 2, the absolute value of 2 minus 1, and that is just going to be 1 minus 3. That's going to give us -2. So the 2 will give us -2. All right. And we can keep doing this and keep getting points here that look about like this. So this is going to be the basic shape of our graph. Let's confirm. We wanted a graph that was down 3. So we went down 3, 2, 3. And we wanted to go to the right one, So there we go. The shape is exactly the same, but we have moved it down 3 and to the right 1. Okay, so that's a little bit about why those rules work. What if we want to maybe shrink or stretch a graph? So let's consider some function f of x. So if we want to stretch the function vertically, right? So if we want to make it look taller, so to speak, it's kind of hard to explain, but we're stretching it vertically. We're making it look look longer in the vertical direction, we're going to graph a times f of x, where a is some number greater than 1, but less than infinity. Multiplying by infinity doesn't make a ton of sense, but some number greater than 1 is kind of what we're looking for here. All right, so if we want to shrink the function vertically, we graph b times f of x, where b is some number that's greater than 0, but is less than 1. So some fraction, some irrational number between 0 and 1. The idea is you want to shrink it a little bit. You want to make it shorter, so to speak. Okay, and if we want to stretch the function horizontally, okay, we're going to graph f of b times x. And again, this is kind of counterintuitive again, but we're going to graph b times f of x, where b is between 0 and 1. So if we're multiplying by a number between 0 and 1, so by a fraction on the inside of the function, that is actually going to make the function stretch. And if we want to shrink the function horizontally, we'll multiply x times a number between 1 and infinity, okay? So some larger number. Let's see why this works with an example here, okay? So let's consider the function f of x equals the absolute value of x, okay? Sorry about that, I have a cuckoo clock in my house. Okay, the graph of f of x equals the absolute value of x is shown here. And we want to graph f of 1/2 x and also 2 times f of x, and just see what happens if we do this, okay? You have some problems in your homework that ask you to do some similar things here, so hopefully this will be of some help, okay? So let's do a little point chart here. So we'll do x, and we'll do f of 1/2 x, which is equal to the absolute value of 1/2 x. Okay? Write this a little neater. Okay. So that would give us 1/2 x on the inside of the parentheses. So let's go ahead and plot the point 0, see what happens. So we get 1/2 times, 1/2 times 0 in the absolute value bars. That's going to give us just the absolute value of 0, which is 0. If we plot the point, so we know that we're going to have a point here, 0, 0. If we plot the point 1, we'll have 1/2 times 1, which is the absolute value of 1/2, which is going to be 1/2. So at the point 1, we're going to have 1/2. If we plot the point -1, we'll get 1/2 of -1, which is the absolute value of -1/2, which is again just 1/2. Okay. And if we do 2, we'll get 1/2 of 2 in absolute value bars, which will just give us 1. Okay. And if we plot -2, we get the absolute value of 1/2 times -2, which is just -1. Or sorry, the absolute value of -1, which is +1. Okay, so that'll be here. So if we connect the dots and draw our graph, it'll look a little bit like this. Okay, so we multiplied the inside of the function. So we multiplied x by 1/2. And so let's see if that checks out with our rules here. So we wanted to shrink. This shows like we're shrinking the function vertically. We're kind of squishing it a little bit vertically. Okay. Or sorry, I guess we're stretching. I guess you could say this is kind of the other one. I guess we're stretching it. So if we stretch it, yeah, so this checks out. So we're multiplying the inside by a number between 0 and 1. 1/2 is between 0 and 1. So this should stretch the function horizontally. It makes it wider. So what we're seeing here is each point, if we see this point here, it goes here, and this point here is going to go here. So we're stretching the function. We're stretching the function vertically, right? So yeah, that's kind of the gist of how that one works. But what if we wanted to graph 2 times f of x? So what we should expect to see here, what we should expect to see here would be, since 2 is greater than 1 and less than infinity, we should see the function should stretch vertically, okay? That should be what we end up seeing here. All right, so if we have x, all right, and we have 2 times f of x, that's going to be 2 times the absolute value of x, okay? Let's see what happens when we plot some points. So 0 will, again, give us 2 times the absolute value of 0, which is just 0. So again, we're going to keep that point. Let's do 1. We'll do 2 times the absolute value of 1, which is 2 times 1, or just 2. So 1 will go here. Negative 1 will give us 2 times the absolute value of negative 1, which is 2 times 1, which is, again, 2. Okay, and you can, again, keep going. So we do 2 as the absolute value of 2. That'll give us 4. And negative 2 will give us the absolute value of negative 2 times 2, which is, again, 4. So the graph is going to look a little bit like this. Okay? So this is somewhat tedious, but hopefully the idea here is that you can take this and maybe more quickly go through your homework by understanding some of these rules a little better and why they do what they do. But yeah, so this did show that we ended up multiplied by a number greater than 1. Okay, on the outside, so that means that we did stretch the function vertically. Okay, so again, this initial point here moved up here. Okay, and this one moved here. So we're seeing it stretch vertically. All right. So that followed our rules. And then, real quickly, I'm not going to, just for the sake of time, hopefully this makes sense and isn't um, one that I have to. Well, we'll go ahead and do one. Why not? Okay, I'll do it here in a second. So let's say we want to reflect a graph across an axis. Okay, so if we want to reflect a graph, say we have some function f of x, y equals f of x, and we want to reflect this graph across the x-axis. We're going to graph negative f of x. And if we want to reflect it across the y-axis, we'll graph f of negative x. Okay. So let's just take our let's do like let's do x cubed. Let's do that. Okay. Come down here. So we gotta erase all this junk. Okay. And if we have x cubed, we're going to get a graph that looks a little bit like this. We plot a few points, 4, 6, 8. So it'll look a little bit like it's really steep very quickly. Okay, 1. Okay, so it'll look a little bit like this. So if we have f of x equals x cubed. Okay, so that's the basic shape of our graph, f of x equals x cubed. And let's say we want to flip across the x-axis. So if we look at our rules, to flip across the x-axis, we're going to graph negative f of x. And negative f of x is just negative x cubed. Okay, we'll put the parentheses around the whole thing, x cubed. Okay, to flip across the y-axis, we'll get f of negative x. Okay, and this will be negative x quantity cubed. And that means we're cubing negative x, okay? Instead of taking the negative of x cubed, we're now cubing negative x, okay? And we'll see why this is important here in just a second. But let's go ahead and plot a few points on this to see why this works. So let's go ahead and do a point plot here for negative f of x. Okay, so let's do the point 0. So we'll have negative 0 cubed, which is just 0. So the point 0, 0 is going to stay where it is. Okay, let's do 1. So we'll do negative 1 cubed. So the negative of 1 cubed. And 1 cubed is just 1. So we'll have negative 1. So 1 is going to go to negative 1 now. If we do negative 1, we'll get negative 1 cubed. And we know that negative 1 cubed is negative 1, but negative 1 is positive 1. Lots of double negatives here, but so we'll get a positive 1 here, okay? So this negative 1 is going to go to positive 1 now. If we do 2, we'll get negative 2 cubed, and 2 cubed is 8, so we're going to get negative 8. Okay, and then predictably, negative 2 will give us negative 2 cubed, where negative 2 cubed is negative 8, so negative 8. So we'll get positive 8. So that's going to go here. So what we're seeing here is for this one, we have flipped across the x-axis. Okay, so this point went here, this point went here, okay, this point went here, and this point went here. Okay, now x cubed has a very interesting property here. Okay, you might be thinking, if we flip it across the y-axis, isn't it going to look the same? Well, let's find out. Let's see what happens. Okay, so if we have x and then f of negative x, which is going to be the cube of negative x, and we plot a few of these points. Okay, we're only going to have to plot a couple of these to see where this is going. If we plot 0, again, hopefully we can all see we're going to get 0. So 0 is going to stay the same. If we plot 1, we'll get negative 1 cubed, which is negative 1. So 1, negative 1. Aha, there we go. If we plot negative 1, we'll get negative 1 cubed, which will give us just positive 1. So negative 1 will give us positive 1. All right, so hopefully you can see if we keep doing this, if we do 2, we'll get negative 8. We do negative 2, we're going to get positive 8. And we can keep doing this, and we're going to see that it's going to give us the same thing back. This is not true for every function, but this is true for x cubed in this case. So that wasn't the greatest example I could have picked. There are some other examples we could do to show different behavior for each of these. But I would encourage you to play with this. Maybe get on some graphing calculator, or I'm sure you'll get to see it in your homework as well. Different examples of what this is going to look like. But this is kind of a longer video, but hopefully this helps you a little bit with understanding what happens with each of these transformations. And I'm going to leave it up to you to try to put these together, okay? If you have any questions at all, please feel free to email me. This can get kind of tricky, kind of tedious, as you can see. Lots of places you can make little mistakes. So don't feel bad if you make mistakes at first. It's not that big of a deal. But yeah, so good luck with everything. And yeah, have fun studying for the midterm.